Hi everyone, my name is Yiting Xiang from University of Connecticut. Today I'm going to talk about my paper, Parameter Identification for Multiple Machine Bernoulli Line using Statistical Learning Methods. Here is the outline. First, I will give a brief introduction. Second, describe our system model and problem. And then I will introduce the statistical learning methods we used. Next, I will show the experiment results. Finally, it is a conclusion and future work. With the development of Industry 4.0, model-based analysis plays more and more important role in manufacturing research. We build valid models to capture the behaviors of job flow in production systems, and then the model-based analysis supports our smart production system. So, using the models, we can make decisions to optimize the production process for some different kinds of objectives, such as increasing productivity, increasing the quality of production, allocation the resource to reduce the total cost and energy, rapid reaction to changes, advanced planning and controlling, and so on. Thus, modeling is essential to model-based analysis and to smart production system. In the process of modeling, parameter identification is one of the most important steps, and this paper focuses on parameter identification. In conventional approach, we first build structural models based on the system layout, and then we collect data from each individual workstation in the physical level and come up with the methods to aggregate data and to extract the model parameters for individual processing steps parametric models, and finally obtain the overall system model. There are many limitations. First, for some small and medium-sized manufacturers, they don't have any automatic data collection equipment, so data collection is difficult to them. Then, in order to get valid machine parameters like uptime or downtime for each machine, we have to spend a long time connecting many enough observations to make sure they are in a high accuracy, and the data we collected is not necessarily in the standard form, so a lot of inconvenient data process work is involved. Finally, there is no standard rule or unique solution to aggregate data or extract the model parameters, so it requires a lot of modeling experience and trainings of modelers. Therefore, we want to develop a new approach to solve these limitations. In our new approach, we use standard performance metrics to identify machine parameters instead of those non-standard from the data. So, our goal is obtaining the parameters which are the best match with the system performance metrics. Moreover, this new approach is much more efficient and convenient because performance metrics data is very easy to collect on factory floor in a short time, and they are commonly used and easy to understand. In addition, the users just need to give the performance metrics as an input, and then we will obtain the machine parameters as output without doing anything else. So everyone in different knowledge levels can handle it easily. In this paper, we focus on Bernoulli serial line model. In the figure, circle is machine and rectangle is buffer, so there are n machines and n-1 buffers in this line, and the buffer capacity is Ni. Pi is the probability that machine I is up. We call it machine efficiency. M and N are the physical data, so they are easy to observe. Pi is the machine parameter which we want to identify. To identify Pi, we use the standard performance metrics, including production rate and working process. Production rate is the average number of jobs produced by the last machine per cycle time in steady state. Working process is the average number of jobs contained in the buffer in steady state. So the basic idea is that we use the performance matrix as input and we obtain the machine efficiency as output by our new approach. In the previous research, we identified Pi by matching the values of P and WIP, so we solve equations based on the closed form expression of P and WIP and aggregation of them. In this paper, a new method is proposed, which is data-driven learning-based method. We train the statistical learning models using simulation data to explore the linear or nonlinear relationship between machine efficiency and the performance metrics by minimizing the mean square error and then using the trained model to estimate the machine efficiency given new performance metrics data. This is an overview of the statistical learning method. We can create a data library offline, which is easy to call. Our training data can come from the data library. They can be experiment data or simulation data. Here we use simulation data. Specifically, we simulate 3 510 machine lines, 5,000 observations for each, and randomly select 4,000 as training data, 1,000 as testing data. In the data set, the variables are related to the performance metrics, including PR, WIP, WIP divided by N in each buffer. Responses are the machine parameters. Then we use 3 different statistical learning methods, including multivariate regression, random forest, artificial neural network to train the data, and use the trained model to estimate the machine parameters of testing data, and calculate the root of mean square error and estimation error to evaluate the model. Finally, if the estimation is valid, we can update our data library. We start from the simplest statistical learning model, multivariate regression, which is a linear model. The basic step is as following. First, we check the correlation between all response and all variables for all 3 510 machine lines. Since WIP and WIP divided by N are correlated to each other, we consider to add two-way interactions between WIP and WIP divided by N into the full model. Next, we do the predictor selection by a combination of forward and backward selection and AIC, and then we calculate the coefficients. Finally, use the model to predict the PI. Next, the learning method is random forest, which is a tree-based method. It can capture linear and nonlinear relationship between the response and the variables, and also can capture the interaction among the variables. The basic construction is as following. Suppose we want to grow a forest of S decision trees. Then we grow each tree on an independent bootstrap sample from the training data. At each node, randomly select Q of the all variables and choose the best split among the Q variables. Finally, we predict new data by taking average of the prediction of the S trees. In random forest, some model parameters need to set up before we train it. The most important two include the number of trees and the number of randomly selected variables. They have a significant effect on the model performance, so we train the models as a grid of parameters to find the optimal ones. Moreover, random forest has a byproduct measurement called variable importance. There are two types. One is mean decrease in node impurity, another one is the mean decrease in accuracy. For each variable, higher value of the importance measurement means higher importance level. Thus, variable importance provides us a guideline of variable selection, although it is not a standard rule. Next learning method is artificial neural network, which is very powerful to solve complex problems. The construction of network we use is a classic one. There are 3 layers: input layer, hidden layer, and output layer. They are connected by the weight. In the hidden layer, there are H neurons, and the activation function is sigma. In order to get the optimal H, we train the model at a grid of H and take the best one for our network. Finally, the output PR is obtained by an output function, which is identity function for regression problem. Thus, the mathematical formulation is like this. To minimize the mean square error, the optimizer we use is PFGS Quotient-Newton algorithm. Although neural network usually has good performance, sometimes it has overfitting issue because there is no standard predictor selection method for it. For instance, overfitting may happen to 10 machine learning models because of those insignificant predictors. In previous sections we see multivariate regression has standard variable selection step and random forest has variable importance measurement. In multivariate regression, those WIP divided n and their interactions far away from that specific machine are eliminated. In random forest, variable importance shows PR and the nearer WIP divided n are more important. This means the response PI is only significantly affected by PR and those WIP divided n close to it. It also makes sense in real-life situations. For instance, it is clear that the data of the first buffer is very important to estimate the efficiency of the first machine and second machine, but it has little importance to the machine 10. Therefore, we just keep PR and WIP n close to that specific machine in the network as input predictors to avoid overfitting and reduce the training time. Here is our result. As mentioned before, we have a total of 5,000 data for each 3, 5, 10 machine line. Among them, we randomly select 4,000 as training data and rest 1,000 as testing data. And we use training data to train the model. We do this repeated random self-sampling experiment 10 times. For each time, the root of mean square error and the estimation error are calculated to evaluate the learning model. Table 1 is showing the average of root of mean square error and estimation error of machine parameters for 3 learning models and comparing with the aggregation-based algorithm. According to Table 1, indeed, multivariate regression models have the worst estimation performance among the 3 learning models because the machine efficiencies are not perfectly linear in variables and in their interactions. Then, the estimation error of random forest is close to the aggregation-based algorithm. Random forest can avoid the overfitting issue even though all variables are included in the model. However, they cannot give the precise, continuous nature estimation, which causes the testing error to be significantly higher than their training error. Finally, the artificial neural network gives the best estimation because they can learn the nonlinear relationship between the input and output very well and performance better in generalization of the models to the testing data. With the estimate parameters, we can get estimate performance metrics by simulation. In Table 2, we compare the average estimation error of the performance metrics. Both artificial neural network and aggregation-based algorithm have low error in performance metrics, which implies our machine parameter estimation can fit the system performance very well. In conclusion, first, 3 statistical learning methods are implemented to estimate the machine parameters of a Bernoulli production system model based on the performance metrics PR and WIP. Then, artificial neural network has the best performance among the 3 learning models and has higher accuracy in parameter estimation than aggregation-based method. Moreover, both multivariate regression and random forest show that when the production line is very long, the machine parameter is only significantly affected by the variables close to that specific machine, linearly or non-linearly. Besides, this learning-based approach is much more efficient and convenient to users than conventional approach because learning model can be pre-trained with simulation data so that machine parameters can be obtained as output immediately when PR and WIP is given as input. For future work, This offline learning model can be transformed to online version, and we can add more variables into our model to increase accuracy. Finally, we can extend to the other production system models such as geometric model, exponential model, and so on. Thank you for your attention.